Hello guys, welcome back to another video. I hope you guys are doing absolutely fine. Now we'll be doing an assignment on multinomial logistic regression and ordinal logistic regression. So let's begin with question 1. Question 1 part A says read the stata data. Now stata data is a software file and we will use Heaven library to read it. We can also use foreign package to read this data, but we are using Heaven library. So we will load the library first. As I have already installed the package, so I have put a hashtag sign and I have directly loaded the library. Now this data is available on the UCLA website. Either you can download the file from the website and read it, or you can directly take it from the internet. So I am using read_dta function to read this file, and I have mentioned the website address here, so it will directly read the data from the website. After this, we will store the data in the variable OData. By the way, this example is given on the website only. So once we have read the data and stored it in the variable OData, we can go on reading the structure of the data. So as you can see, the structure of the data is printed here. Now we can read the explanation of the structure of the data given here. So first point says there are 4 variables here. Then second point says the apply variable is an ordered categorical variable with responses to a survey from the students. The responses were about whether a student feels that they are unlikely, somewhat likely, or very likely to apply to graduate school. Unlikely is given by 0, somewhat likely is given by 1, and very likely is given by 2. Then the third point says the paired variable is a binary variable indicating if at least one parent has attended graduate school. Next point says the public variable is a binary variable indicating if the undergraduate institution is public as opposed to private. Then the GPA variable is the undergraduate GPA. Next point says notice that the order of the values in apply correspond to order of the variable. Then the next point says we will use POLR function, which is proportional odds logistic regression, for doing OLR. This function is in the mass package. Now we will move to question 1b, which says perform ordinal logistic regression. So we will first load the library. Then we will convert the apply variable to factor variable. We can simply use the $sign to subset the apply variable from our dataset, and then simply use the factor command on the subsetted variable to convert it into the factors, and then store it in the dataset in place of the original variable. This way, original apply variable will be replaced by the new apply variable, which is a factor. Now we are good to go to build the model. So just like other functions, the first argument is the variable followed by a tilde and a dot, and then the second argument is the data. We will run it and store the results in the variable model. After this, we will use summary function to check the model summary. So let's read the explanation given here for the summary. So the first point says, if we see we have 2 intercepts. The reason for this is that our variable apply has 3 levels. So R has created a dummy variable as unlikely and somewhat likely. And the second dummy variable has 2 levels, somewhat likely and very likely. So we will have 2 equations as above with the same coefficients, but intercepts would be different. Then the third point says we have AIC and RD given, which can be used to compare different models. We can also write the equation as shown here. So as I said earlier, there would be 2 equations. The equation 1 would be for dummy variable that has 2 levels as unlikely and somewhat likely. And it can be interpreted as log of odds of believing that students are unlikely to apply to grad school versus somewhat likely. So we can write the equation as logic probability y is less than equal to 1 is equal to 2.2039, which is the intercept, as given in the summary minus 1.047 into the paired variable minus again a minus sign 0.0587 into the public variable minus 0.615 into GPA. Now the second equation would be for the dummy variable that has levels as somewhat likely and very likely. And it can be interpreted as log of odds of believing that students are somewhat likely to apply to grad school versus very likely. So we can write the equation as logic, the probability when y is less than or equal to 2 is equal to 4.2994, which is the second intercept, minus 1.047 into paired minus bracket open again a minus sign 0.0587 into public minus 0.615 into GPA. So that is how these two equations are written. Now we can use the above equations to calculate the desired probabilities by simply taking the exponential or anti-log of it. So probability of y being equal to 1 can be calculated from the first equation, which says probability of y being less than or equal to 1. And probability of y being equal to 2 can be calculated by the probability of y being equal to less than or equal to 2 minus the probability of y being equal to less than or equal to 1. And similarly, probability of y being equal to 3 can be calculated 1 minus probability of y being equal to less than or equal to 2. So that's how we interpret these equations. Now moving to the next part, it says calculate the probabilities. Now there is a small note given here. It says we can skip the above math using the predict function for our new or test data. But as we have not divided the data into train and test part, so let's take one observation from our data and find these probabilities. So the predict function has the usual arguments. The first argument is the model. The second argument is the test data. But in this case, we don't have our test data. So we will give our original data. Now from the original data, we are only giving one observation here, just to demonstrate the process. And then we'll mean type is equal to P. It means it will return the probabilities. And then we are also rounding it to 3 places of decimal. We will run this and we'll get our probabilities as shown here. Now if you have noticed above, our model does not return the p-value to know the significance of the variables. So we will calculate it manually. So let's see how do we do it. Now pt function is similar to pnorm function, but it is for t distribution and uses the degree of freedom to calculate the probability. So the first argument is the t value. So we can calculate for any variable. Here we are calculating for the paired variable. Then add the degree of freedom, which is total observation minus total variable, and mention lower tail is equal to false. And then we are multiplying it by 2 as it's a two-tailed test. So if you see the summary, 3.94 is given as the t value for the paired variable. Now remember, our hypothesis is that at least one of these coefficients is not 0 or is not significant. So we are testing equality here, and that is the reason it becomes a two-tailed test. Now we can run this and our p-value is calculated. In the similar way, we can do this for all the remaining variables and can calculate the p-value. Now let's see how we can do it using the pnorm function. But for using the pnorm function, we will first store the coefficients and the intercept in the variable summary underscore table. So we will use CUF function, give the output of the summary of our model, and this will store the coefficient and intercept in the variable summary underscore table. After this, we will use the pnorm function. We will simply subset the t values stored in the summary underscore table Remember the t values are given in the summary output, so we will just subset it and extract the t values. Then we will use ABS function to return the absolute value irrespective of the sign. After that, lower tail is equal to false, and then we'll multiply it by 2 as it is a two-tailed test, and we'll store this in a variable called pval. Then to print the p-value alongside the t-value, we can simply combine the output given in the summary underscore table variable with the output stored in the variable pval. So we can use the cbind function and combine the columns of summary underscore table and the variable pval. After this, we can print this, and here you can see the coefficients, the standard error, the t-value, and the p-value is printed. Now from the p-value we can see that the variable public is insignificant. Now there is a rule of thumb as well which can be used instead of doing all these things. It says with degrees of freedom over 100, we can also just say that any t-value over 2 is statistically significant, at least at the 5% level. Now we will move to next question. It says interpret the coefficients. To interpret the coefficients, we will have to convert them into odd ratio as they are currently scaled in terms of logs. To convert it to odd ratio, we simply take the exponential of the coefficients and then interpret them simply the way we do for any logistic regression. So here we have taken the exponential and printed our coefficients as below. Now let's interpret the results for any one variable, say the paired variable. So for the students whose parents did attend college, the odds of being more likely, that is very or somewhat likely versus unlikely, to apply is 2.85 times that of students whose parents did not go to college, considering all the other variables are constant. Similarly, for students whose parents did not attend college, the odds of being less likely to apply, that is unlikely versus somewhat or very likely, is 2.85 times that of students whose parents did go to college, considering all other variables as constant. So that is how you interpret the coefficients. In the same fashion, you can interpret other coefficients as well. Now moving to the next question, it says perform multinomial logistic regression. Now let's read in the data using this link and store the data in the variable mdata. Then we can read the structure of the data. Now the explanation of the structure of the data is given. So let's read the explanation. First point says there are a bunch of variables in this data set, but we only care about 3: PROG, SES and write. The first variable PROG is a categorical variable indicating what type of program a student is in: general, which is 1, academic, which is 2, or vocational, which is 3. The third point says the SES variable is a categorical variable indicating someone's socio-economic class: low given by 1, middle given by 2, and high given by 3. The write variable is their score on a writing test. Now in the next step, we will convert the PROG and SES variables to factor variable. So we have already seen above how can we convert any variable to a factor variable. So I will not explain it again. After converting it into factor variable, we will proceed to performing MLR. But before performing MLR, we will first have to understand how MLR works. So let's refer to question 2b, which answers this question. Now point 1 here says MLR reports the outcome categories in reference to some base group. For example, in our case, the dependent variable is PROG and it has 3 categories: general, academic and vocational. So we will make general as the base group. We could select any one, but we will have to make one category as the base group. So in this case, we are selecting general as the base group. Now as there are 3 different categories, so MLR will give 2 different models as below. Model 1 would be logic, probability of program being academic, or general is equal to rest of the logistic regression equation. Similarly, model 2 would be logit, probability of program being vocal or general is equal to rest of the logistic regression equation. So for 3 categories, we will get 2 different models. Now we'll move to question 2c. It says, how do you set the reference group in R? So we will use RE_level function for setting the reference group. The first argument would be the variable, which is the dependent variable. And the second argument would be the category, which needs to be set as the reference group. So here the first category refers to general. And then we'll run this and store it in the variable mdata$prog, which will basically replace the prog variable in the original dataset with these new values. Now we can move on and perform MLR. So first we will install nnet package. Now as I have already done it, so I have put a hashtag sign and I am directly calling the library. Then we will use multinom function and write the formula. prog is the dependent variable, then a tilde sign followed by the rest of the 2 variables, which is ses plus write. Now in this case we have many variables and we don't want to use all the predictors. That is the reason we have mentioned the names of the variable instead of mentioning a dot. And as usual, the second argument would be the data, which is stored in the variable mdata. We can run this and we'll store the results in the variable model.mlr. After this, we can check the summary of the model using the summary function. Now if you see the summary here, it is divided into standard errors and coefficients. Also on the left hand side, 2 and 3 are given under coefficient and standard error. This basically means the 2 models as I explained above. Model 2 is probability of being academic versus general, and model 3 is equal to probability of being vocational versus general. Now again, coefficients are given in log odds. We can use the same transformation as we did above to interpret them. And we also have AIC and RD to compare the models. So that is how you interpret the summary. Now to interpret the coefficients, we will again convert them into odd ratio by taking the exponential. Now I have already explained above how to interpret the coefficient, so I am skipping it. Now let's move to next question. Question 2D says, determine statistical significance of our coefficients. Now there is a small note here. It says MLR model does not give t values like we had in OLR. So we cannot use it to find p-values. Therefore, we will use standard error, as we know that z value is equal to coefficient divided by standard error. So we can calculate the z values using the standard error. So first we will extract the coefficients by subsetting the summary output, and then we will divide it by standard error, and again we can extract the standard error from the summary output of our model. We can run this and now we have the z values. Now we can calculate p-values using the z values by using the pnorm function. So the first argument is the z values. We will use the absolute z values, so we will use the ABS function. Then lower tail is equal to false, and then multiplied by 2. We will run this and we will get our p-values. Now we can either interpret the significance based on the p-values, or we can use the z values by using the rule of thumb. What is the rule of thumb here? Well, we know that the z value or t value is generally equal to the point estimate divided by the standard error. And we also know that a value of over 2, when you have large degrees of freedom, generally means statistical significance at the 95% level. Therefore, we can conclude the following. If the point estimate is more than 2 times the standard error, the coefficient is statistically significant. So this is our rule of thumb. So with this, we have come to the end of this assignment. In this assignment, we have learned how we can perform these two methods, MLR and OLR. We also have calculated p-values to find the significance of these variables using t-values and standard error. So guys, I hope you have gained some insights from this video and have found it useful. We have one more topic left in this module, that is sampling methods. So I'll see you in the next video. Until next time, have a great day.